Okay, so this is the last portion of this course, this particular chapter, and what we want to discuss is today is the Blasius integral law, and we'll also go over something called the Kutta-Jaworski theorem. Now, for this particular portion, I'm going to follow a slightly different reference text, okay, and I'll just give out the name of this text for you if you want to look at it, and that is Fundamental Mechanics of Fluids by Curry. Okay. If you wish, you can take a look, and it explains the Blasius integral law rather clearly, and that's why I'd like to take a look, use this particular text. So the topic at hand is something called the spelling is wrong, Blasius integral law. And this integral law deals with the generalization of the drag and the lift that we have just encountered. And we encountered it for the very special case of a cylinder, but now we want to consider a more general case. So let us consider a 2D incompressible, we know the drill, right? What's going to come next? It's also inviscid in this particular case, and steady and irrotational. Flow around an arbitrary body. Okay. So let us consider an arbitrary body in a flow field, and there is a flow field, and let us consider a fixed control volume with a contour C, a C naught standing for C outside, and another contour which just envelopes this body, and that was labeled Ci. Okay, and let us also define our axes very clearly. So the axes are this is this is X and this is Y. Okay, now my drag force and the lift force my drag is going to be along X and my lift on the body is going to be along Y. Now this situation is such that the drag force on the body is obviously going towards the right, but the force on my on the fluid is now going to be towards the left. So my drag vector will point in this direction, and similarly my lift with respect to the fluid will point in this direction. With respect to the body, it's in the opposite direction. Okay, so now we are going to consider inviscid flow. So we are going to neglect viscosity, and we are now going to consider the x momentum and the y momentum equations for this particular case. So now the forces can be written such that you have minus d p dy equal to integral rho uy dx. And the reason this comes out to be of this form is because this when you integrate the pressure on the inner contour, you end up getting minus d, and this is the other one. But we should show what the pressure etc. looks like. So for the outer contour, which is where it is important, my differential surfaces are such that this is my dy and this is my dx, let's say at a given location, and my ux is in this direction and my ui is in this direction, right, if I consider all them to be positive. But my pressure, interestingly, is always pointing inwards. Okay, so once you realize what these directions are, they will end up becoming this particular term. Okay, so this is for so there is no mass transport across the inner surface because there is this body, and therefore the integral of pressure is going to be d, and we have the pressure on the outside and the flux here. There is no flux in the inner one to consider. Okay, oh, I have missed something. This is over C0, okay, because there is no mass flux in the inside body portion. So the other equation will now look like this is C0 and this is P dx equal to my integral again over CL, and this is momentum in the y direction, which is uy, and rho uy dy minus rho ux. This is rho ux dy minus rho uy dx. Okay, now from Bernoulli's equation, if you neglect the gravity portion, okay, we have been doing that for the past some time, so neglecting gravity, you can see that we can say that P plus half rho ux square plus rho uy square equal to some constant, or this constant or pressure now is equal to some constant minus half rho ux square plus uy square. So now you introduce this value of pressure for d, so replace this pressure right here into this and then obtain an expression for d. So then d will end up becoming this integral of CO, and here you'll have many terms, so let's write them carefully. It will be minus C dy plus half rho ux square plus uy square dy minus rho ux square dy minus ux uy dx. And for lift, my should be C0 C dx minus half rho ux square plus uy square dx minus rho ux uy dy minus uy square dx. Okay, now note that whatever be the constant, okay, this quantity, be it integral around dx or with dx or dy, this is always equal to 0. Okay, so your first term can be neglected in both cases. So that equation simplifies a little bit. Now, so you have the drag and the lift in terms of the velocities. Now consider the term I rho by 2 integral C0 df dz square into dz. This quantity is nothing but I rho by 2 integral over C0 ux. We have already said what df by dz is, which is ux minus I uy, and this is dx plus I dy. Okay, so I'm sorry. Just a second, get some water. Okay, so now let's open this up, which is I rho by 2 integral C0. You have ux square minus 2I ux uy minus uy square dx plus I dy, right? Okay, so this, if you open this up further, you bunch the real terms and the imaginary terms together, and what will come out to be is, if you take this inside, okay, so I'm skipping a step here, and if you take everything inside, then you will get the real term to be rho ux minus uy square dy plus rho ux uy dx, and the imaginary part to be minus half rho ux square minus uy square dx minus rho ux uy dy. Okay, so this is what you will get, and if you compare with your previous write-up, what you will see is that this is equal to d and this is equal to L. So if you substitute, you end up getting I rho by 2 integral C0 df dz square dz equal to d minus IL. Okay, and this is the I always write this u, that is not correct. The Blasius, u is later, Blasius integral law. Okay, so this is a rather important law, which is related to the idea that the drag and the lift that we had considered, we are now making it a little bit more general, and that's why this new form, that's why you have to compute this all over again. But what we see is that the drag and the lift can again be written in a very simplified format if we especially use the complex form, and this now is a very simple integration to do. But unless you know complex integration, then this is not that easy to do. But if you do know how to do integrals for complex numbers, then this does become easy. Now the next part of the theorem, which is the Kutta-Jaworski theorem, that does involve integrals and some knowledge of how to evaluate these integrals. I'm not sure if all of you know that complex analysis, and we are not going to be using that too much in this course. So I will just state the other important theorem, which is the Kutta-Jaworski theorem. And the Kutta-Jaworski theorem says that consider the flow around an arbitrary closed body. Okay, let's say it's, for our sake, centered at the origin in a uniform stream flow, just like what we took. And far away from the body, the complex potential will be in a certain form, and so far away from the body, the complex potential Fz can be written as uz plus m minus I tau by 2 pi log z plus integral of 1 to infinity bn z to the power n. And this, once you have this complex potential, you can apply the Blasius integral law. So apply Blasius law, and df by dz in this particular case will end up becoming u plus m minus I tau by 2 pi 1 by z plus integral to 1 to infinity, and you have minus n times bn and z to the power minus n plus 1, right? So now you can calculate df dz square, and this will have a lot of terms now, of course, because this goes off till infinity. Now what ends up happening is you need to consider some of the first terms, and then we'll bunch all the terms which are order z cube together. So the first term is u square, and then you have 2 m minus I tau by 2 pi u by z. Okay, so that's the second term, and then you have another term which will be a 1 by z square term, and this should look something like this. This is square 1 by z square plus order of 1 by z cube terms. Now if you use the residue theorem, okay, so there is something called the residue theorem in complex integration. Using residue theorem, you can evaluate this integral, and what comes out is this integral I rho by 2 c0 df dz square dz, and I'm just going to state to you the result. Comes out to be minus rho m u plus I rho u tau, and so now for a closed object, so for a closed object, this m is 0, and that's why your drag turns out to be 0 and lift turns out to be minus rho u tau. And this statement is also referred to as the Kutta-Jaworski theorem, and for if you have open system, then you can apply it again here, and you can get the answer. So this is an important theorem that is used, and but it uses quite a bit of knowledge of complex numbers that I'm not really sure that I should be expecting for all of you to be very comfortable with. So I just stated this result, and I'm going to leave it like that. And with this, we sort of end our discussion on complex potentials, and we still have a few short topics left to discuss. One is the energy theorem, the integral form of the energy conservation. And what I'll do is I will be recording some other lectures, and I'll be giving those to you as separate lectures for you to listen to. Okay. So for today, I'm just going to end up here.